So welcome back. So in our previous discussion in section 10.1, we were discussing two independent samples, but a lot of times we don't have two independent samples. In fact, we don't want two independent samples. We're trying to test a change that has occurred, and so we want to test the same sample, maybe either over time or a before and after. And so this is called a matched pair. And so when we're testing a matched pair, we're testing the mean difference. So the difference is the x1 minus x2, the sample 1 minus sample 2. So we're testing that the mean difference, that D, is either equal to 0 or not equal to 0 or whatever. So we're testing that. In order to do this, we need to make sure that the difference is normally distributed, or both sample sizes, again, are greater than 30, according to the central limit theorem. So in a matched pairs experiment, it's kind of important to recognize this. Again, before and after studies, maybe we want to measure the weight loss of clients before they did our diet plan, and then after they did our diet plan, or measure the weight. Maybe we want to measure the effectiveness of a particular drug, so we're going to test our particular medicine. So we're going to test patients before they take our medicine, and then after, maybe we're going to test the effectiveness of this medication in bringing down a fever, or something of that nature. Or it could be paired observations where it's not the same individual who gets or the same thing that gets sampled twice. Maybe it's not an over time, but maybe we're going to split it into two groups. So you have one group that has like the placebo, or one group gets, for example, this type of painkiller, and the other group gets a different type of painkiller, and then we're comparing the two. So again, they're not independent, but we're testing them together. Now, we are going to use those same z-test and t-test to calculate these, really t-test to calculate these. We've got our same confidence intervals, and again, you can see the confidence interval here, which is the mean of the difference plus or minus the t-score multiplied by the standard deviation, divided by the square root of the sample sizes. Now, our hypothesis tests are just like we've seen before. So our null hypothesis test always has the equality in it, and the alternative doesn't have the equality. So typically we're testing that the difference is equal to 0, so that's that D sub 0. But if it's a two-tailed test, then we're testing that does it equal 0 or does it not? So is there no difference in the means or not? Or maybe we're looking at a right-tailed test where we're seeing if the mean is greater than 0, or a left-tailed test where we're seeing if the mean is less than 0. Now, does it have to be 0? It could be, 5 or 10 or 25 or whatever we wanted it to be. It's just that 0 is kind of the norm. So again, we're going to look at our t-test here, and we're of course going to do this in Excel. So let's look at our problem here. Now, if you've read in your book, this is the sample problem that they give us at the beginning of the chapter. So a new local ordinance has required that chain restaurants post caloric information. And so we're wanting to test and see, after this caloric information is posted and readily available, does it make a difference in what people order? So the nutritionist has examined, I believe this was for Starbucks, she's examined transaction data for 40 customers before the ordinance went into effect, when there was no caloric data given, and then the same 40 customers after the ordinance went into effect, and did what they ordered change? Did seeing how many calories are in that mochaccino actually make you decide to order something different? And can she conclude at a 5% significance level that the ordinance actually reduced average drink calories? Now we're going to be back in our Excel spreadsheet, but notice here, I'm going to show you this, and we're going to walk through this in Excel, of course, but now we're going to use the t-test for paired sample means. So that's the one we didn't use before, and I mentioned in the video for 10.1 that we would use that later on. So let's jump over to Excel and actually work this out. So I'm in Excel now. I'm in my Chapter 10 workbook. I've got my food calories worksheet pulled up. I've got my data tab up top, and I'm going to go over here to the data analysis. Now, again, we've used the other three here, the 2T test, assuming equal variances and unequal variances. We've used the Z-test, but those were all for independent random samples. Now that these are paired, I want the T-test for paired sample means. So I'm going to say, okay. So I've got my data for variable 1 in range A1 through A41, and my data for variable 2 in B1 through B41. My hypothesized mean difference is 0. I've got labels. I've got my significance level at 0.05 and my output range at D1. So I'm going to press OK. Now this looks just like it did before. Again, the difference is that we have this paired sample means. So notice our means. Before the ordinance, the average caloric drink had 400 calories, or I should say the average drink had 400 calories, and after the ordinance, it had 391 calories. So a little bit lower, but is statistically significant. So here we have our test statistic, our t-score. Now remember that this is a two-tailed test. We're just seeing, sorry, this is not a two-tailed test. This is a one-tailed test. I said that backwards again. We're looking at a one-tailed test. So I'm going to look at my p critical value here for a one-tailed test because my null hypothesis has a less than sign in it. And so since this is 2.15 to the 8th, again, that has many zeros in front of it. So we can say with 95% confidence or a 5% significance level that we can reject the null hypothesis and that the caloric drink intake did decrease after the city ordinance.